All right, good morning. Just kind of picking up where we have left off with complex roots, and we have from page 81. Okay, we have equations. Okay, that are quadratic, and we have with the first one. Okay, we have 4u squared plus 64 is equal to 0. And there are varieties of approaches which you can look at solving for u. Okay, so right now we have a single variable term with 4u squared. Now you can either factor out 4 or divide the equation by 4, or you can proceed immediately by isolating 4u squared, which I think we're going to do here. Okay, so if I undo the adding of 64 by subtracting that amount on both sides, so we have 4u squared is equal to minus 64. Okay, so you have the u squared term by itself, and if I take care of the coefficient 4 by undoing the multiplication, so upon dividing both sides by 4, so we now have that u squared is equal to negative 16. And we have, with this setup, okay, utilizing the square root property of equality. Okay, so I have x squared equal to p represented by u squared is equal to negative 16. So if I go from u to the second to u, again, you have with the second degree in u, okay, that signals that there could possibly be two solutions. And in this case, there will be with complex terms. Okay, so we have u is equal to plus or minus the square root of negative 16. And now while the square root of 16 is 4, that of negative 16 is going to be 4i. So we have u equal to plus or minus 4i. And again, if we separate, okay, so you have 4i as well as negative 4i. Okay, all right, so I have two solutions, okay, and both of these are complex terms. And we're going to have somewhat a bit of history to repeat for number 58. Okay, this time, okay, we are looking at solving for the variable p. Okay, and this time we have 8p squared plus 72 is equal to 0. Okay, so we have a quadratic equation once again. Okay, different letter, but you have in standard form once again where the only variable term is p squared. So we have a quadratic equation standard form, and we don't have a trinomial. Instead, we just have a multiple of the sum of squares, just like what we had in 57. And just like what I did with 64, I'm going to do the same thing to 72. I'm going to take that away so as to isolate the variable term in the equation. So we have, in this adjustment, okay, I have 8p squared equals minus 72. And isolating p squared, so if I divide both sides by 8, so I'm going to have p squared is equal to negative 9. And going from p squared to p, so that p is equal to plus or minus, okay, the square root of negative 9. And just like negative 16, I have a negative 9, okay, the opposite sign of a perfect square. Square root of 9 goes to 3, and for the square root of negative 9, this will go to 3i. So we have with p, okay, I'm going to have additive inverse complex solutions again with positive and negative 3i. Okay, so both 57 and 58, okay, we have only one variable term. And just shifting gears, okay, now we have with the next mentioned problem. Okay, so we're changing up the variable going from u to p, and now we're looking at solving for t. And in the case of number 61, instead of just a single variable term, we have two variable terms in the letter t. So here we have t squared minus 8t is equal to negative 24. Okay, so you have a quadratic equation, and unlike the presentation for what we had in the first two items had the standard form, that is the equation, already set to 0. And if I modify what I have here in 61, getting this into standard form, I will add 24 to both sides. And so we have t squared minus 8t plus 24 is equal to 0. And so we have a trinomial expression. Now, one might attempt to factor and might think of factoring by grouping, but here we have, think of like 1 times 24. Okay, so you have 24. However, with numbers that will go into positive 24, there is no combination that will add up to the middle coefficient, negative 8. You might think of numbers like negative 24, negative 1. Well, that sum is going to be negative 25. You might think of negative 12 and negative 2. Well, that sum comes out to negative 14. And you might have like negative 8 and negative 3. Guess what? That adds up to negative 11. And then we have as a last attempt, grasping for straws, you have like negative 6 and negative 4. Well, guess what? That combination adds up to negative 10. Okay, so there are no real integer combination factors 24 that will add up to negative 8. So we're going to have as a recourse, okay, we can utilize, okay, the quadratic formula. Okay, so we have for t squared, okay, we are referencing 1t squared. So we have a is equal to 1. And with the subtraction of 8t, okay, we had that b is equal to minus 8. And we have with 24 added, okay, so we have that c is equal to 24. Okay, now we're looking at solving for a different letter. We have t as opposed to x, and upon utilizing, okay, the quadratic formula, again, we're solving for a different letter, but we still had the same premises applied for the applications of a, b, and c. Okay, so we have with negative b, okay, so we have the opposite sign of negative 8. And we have plus or minus, okay, we have the square root. Okay, so we have with b squared, okay, so we have the square of negative 8. And we have minus 4 ac, so we have times a, which is 1. And we have times c, which we have at 24. Then we have all over 2a, which we have at 2 times 1. Okay. And just for the activity, especially inside the radical, okay, so we have negative 8 squared, which will be positive 64. And then we have negative 4 times 1 is negative 4. Negative 4 times 24 is going to be negative 96. And we have the difference, okay, which will be negative 32. And just taking what we have in the square root of minus 32, So we have just the incremental breakdown. Okay, so we have the square root of negative 32. So we have the square root of 32i. And 32 is not a perfect square, but it is the multiple of perfect squares. And among the perfect squares, we have 4 and 16 that will go into it. So the highest perfect square divisible into 32 is going to be 16. And so we're able to reduce this radical for the square root of 32i will become 4 times the square root of 2 times I. Okay. And so just relaying this over to the next step. Okay, so we have what is going to be positive 8 plus or minus 4 times the square root of 2 times I. And we have all over 2. And if you notice, we have even leading coefficients throughout. We have 8 at the front, 4 in front of the square root of 2i, and we have 2 in the denominator. Okay, so I can simplify. 8 divided by 2 becomes 4. And we have plus or minus, and 2 will go into 4 square root of 2i, 2 square root of 2i times. So this will be the compact notation for the solutions we have in the variable t. And again, we can separate the terms. We'll probably have 4 plus 2 times the square root of 2 times I. And you can also have 4 minus 2 times the square root of 2 times I. And just like in written work, you could have the I in front of the radical, like 2i square root of 2. All right, now for what we have in the case of the next item, we have what's going to be another quadratic equation. Okay, and so we're sort of going all over the place in terms of what variables to solve for. Okay, so we're going from u to p to t, and now in 68, okay, we're looking at solving for m. And for this one, we have m times, okay, the quantity of m plus 10 is equal to negative 34. And again, there might be a tendency to set m and m plus 10 equal to negative 34, but you do not apply the zero product property methodology unless the equation is set equal to 0. So we're going to have to reconfigure the expression we have in m. Instead of writing as the product of m and m plus 10, we're going to have to distribute and sort of untangle what we have on the left. So we're going to remove the parentheses. And we have upon distributing, okay, so you have m over the quantity of m plus 10. Okay, this will be m squared plus 10m is equal to negative 34. And then we have adding 34 to both sides. So we have m squared plus 10m plus 34 equals 0. Okay, now so we finally have the quadratic equation in standard form, and sort of parallel to what we had with t earlier, we don't have the capability of factoring into integer coefficients, where there are no factors, just as there were no factors of 24 that will add up to negative 8. We're not going to have factors of 34 in real integers that will add up to positive 10. You think of like 34, 1, 17, and 2, and that's it. So there's no combination that will add up to 10. So we have, again, just applying, again, the same recourse through the quadratic formula. Okay, so setting up our A, B, and C. A is at 1, B is at 10, and C is at 34. So just taking what we have here, again, just reapplying the quadratic formula. So you have negative b, we have negative 10. We have plus or minus the square root. Okay, so b squared. Okay, we have 10 squared. And we have minus 4 AC. So you have minus 4 times 1 times 34. We have all over 2a. So you have 2 times 1. And now for what we have inside the radical. So we have 10 squared is 100. Negative 4 times 1 times 34 will be a minus 136. And here we will have a negative difference with minus 36. So we will have the square root of negative 36. 36 is a perfect square number. So the square root of negative 36, we have the square root of 36i, which is going to go to 6i. And so just kind of putting this back. So we're going to have negative 10 plus or minus 6i all over 2. And so for what we have, again, we have even valued leading coefficients. Okay, so negative 10 plus or minus 6i are both completely divisible by 2. So we can say we have negative 5 plus or minus 3i in the compact notation. And once again, if I draw out separately, so we're going to have negative 5 plus 3i, as well as negative 5 minus 3i. All right, now we're going to be looking into other types of equations shortly. Okay, and now sort of similar to what we had with the first two items. Number 71, we have just going back to a single second order variable term. Okay, and we have now going to solving for x. So we have 9x squared plus 49 is equal to 0. And kind of like what I had with 57 and 58, okay, I can isolate the variable term upon taking away the constant that is added from both sides. Okay, so if I deduct 49 from both the left and right hand sides of the equation, so we're going to have 9x squared is equal to negative 49. And if I go from 9x squared to just x squared, so we have upon division by 9, we're going to have that x squared is equal to negative 49 ninths. And with the reapplication of the square root property of equality, so we have that x is equal to plus or minus the square root of negative 49 ninths. Okay, and I'm just going to extend this a little further. Okay, so we have the square root of a negative. And so I can draw out the letter I. Okay, so I have the square root of 49 ninths I. And for x, okay, we have plus or minus. Okay, now 49 is a perfect square, 9 is also a perfect square, and the square root of 49 over 9, that is going to be 7 over 3. And so we have in our solutions, we have x is going to be plus or minus 7/3 of I. And again, I can just draw out the results. So you have 7/3 of I, as well as minus 7/3 of I. Okay. Alright, so for this particular set of problems at this stage, we've had exclusively complex roots. Okay, when we started out, we had where there were conditional equations, we've had exclusively real roots, and now we've crossed over to conditionals that have complex roots. Now there will be those equations that will have a blend of both types of roots, that is real and complex. And one category, okay, is going to be what are referred to as equations that are quadratic in form. Okay, and essentially for equations quadratic in form, okay, they will not be quadratic equations in the purest sense, but you're going to see a bit of a 2-to-1 ratio pattern among the exponents. And for equations quadratic in form, now it could be where you have a single variable term, but let's say that just for the heart of the matter, just kind of taking a somewhat generalized case for equations quadratic in form. We say that those are going to be equations where if there are two terms, not that there will be, but say if there are two terms, if we have two terms in the variable, and the dependent variable, that is the variable you're looking at solving for. Okay, so you have equations where if there are two terms in the dependent variable, then the higher order term will be twice the order or twice the degree of the lower order term. And not necessarily just term, but it can also be expression. But here, okay, so just placing emphasis, so you have twice the degree. And just examples of equations that are quadratic in form. And I'll just kind of take some here, not to solve for at this stage, but just want to give you examples here. If you have, let's say, x to the fourth plus 19x squared minus 5 is equal to 0. Notice the degrees in x. We have x to the fourth, x to the second, and if you notice, okay, with the degrees, you have a 4-to-2 ratio, which will go to 2. And so for this equation, this is an equation that is quadratic in form. So we would say that the equation is going to be quadratic in x squared. And let's say that if I have an equation, we'll say that we have something like negative 3 x to the sixth minus 17 x cubed plus 55 is equal to 0. So you have, looking at the degrees in the variable terms. Okay, so you have higher order, we have at 6, lower order we have at 3. And we have 6 to 3, okay, that is going to be at 2. Okay, and so we can say that for this equation, okay, this would be quadratic in terms of the lower order variable factor. Okay, so in this case we have this equation is going to be quadratic in x cubed. And we'll say we have as another case, if I have something like 5x minus 2 times, okay, the square root of x plus 7 is equal to 0. Now again, another way to write this. So you have 5x. Now for the square root of x, if I wrote this as an exponent, okay, so you have 2 times x, or minus 2 times x to the 1/2 plus 7 is equal to 0. Again, just re-emphasizing, you have like the nth root of a to the m is equal to a to the m over n. Let's say for the square root of x. Again, square roots, you have implicitly that the index number is going to be at 2. And x, if I were to express in exponential form, you have x to the first. And guess what? You have a is represented by x, and m over n becomes 1/2. And notice, okay, we have for the comparison of the degrees. So you have from 5x, I have the degree at 1. And from the square root of x, I have the degree in x to be at 1/2. And 1 divided by 1/2 is going to be 1 time. Or 1 multiplying the reciprocal of 1/2. So that is going to go to 2. And this equation, we can say is going to be quadratic. Say the square root of x, or quadratic in x to the 1/2. Okay. All right. Now for equations that are quadratic in form, okay, so you might have varieties of degrees, and if you have, say, a couple of variable terms, again, you're going to have the higher order variable is going to be, or the higher order variable expressions be twice the degree of the lower order. Okay, just like these 3 cases here. And if we have, just taking as examples, if we're looking at solving for x, and we'll say that we have, for instance, okay, if we have, let's say we have x to the 4th, and we'll say that we have, let's say we have x to the 4th plus, and let's say we have x to the 4th plus 3x squared minus 4 is equal to 0. Okay, and just sort of emphasizing, you know, the highest degree, okay, or the higher degree in x in case you have 4. So like if this is a conditional, okay, you have, not that there will be, but whatever degree you have in the variable you're solving for, the higher or the highest degree is going to indicate that you might have up to that many solutions if the equation is a conditional. So you have possibly 4 solutions. And in terms of creating a pathway, so you have x to the 4th plus 3x squared minus 4. Now this equation, notice you have a 2-to-1 ratio between 4th degree and 2nd degree. So this equation will be quadratic in x squared. And I can factor this trinomial. Okay, just as x squared factors to x and x when we were looking at purely quadratic equations and setting up the zero product property, we have with x to the fourth. That times itself, that would give you x to the fourth. It will be not x and x, but x squared and itself. And so we have with the factors of -4, whose sum or difference will be on the plus side at 3. Okay, we're going to have signaled that more weight will be given to the addition than to the subtraction. Okay, so I have x squared plus 4 times that of x squared minus 1 is equal to 0. Now with both of these, I can set both x squared plus 4 and x squared minus 1 equal to 0 and follow through. But if you want to look at completely factoring in terms of integer real coefficients, we have with x squared plus 4. Now, it can factor a difference of squares, but you cannot factor into real integer coefficients the sum of squares. Okay. Now for x squared minus 1, we have a case of the difference of perfect squares. And you can factor in this case where x squared minus 1 goes to x plus as well as x minus 1. So we have 3 factors here, one in second degree and the other two first order. And if we set equal to 0 all of x squared plus 4 as well as x plus 1 and x minus 1. Again, we have upon setting equal to 0. So for x squared plus 4 equal to 0, if I take 4 away from both sides, we have that x squared is equal to -4, and then we have applying the square root property of equality. Okay, so you have x is going to be plus or minus the square root of -4. And so you have plus or minus. Now we have the square root of -4, so this will go to plus or minus 2i. Now for x plus 1 equal to 0, if I take 1 away from both sides, so we're going to have that x is equal to -1. And if x minus 1 is equal to 0, then we have upon adding 1 to both sides, so we're going to have the x is equal to 1. And so I said we might have 4 solutions. And with the way that the cookie crumbles, we do have this to come about. So we have with our solutions, okay, so we have 2i and -2i, as well as negative and positive 1. And if you notice, now before we had with conditionals, we've had exclusively real valued solutions, and then most recently we had complex number solutions. And now for equations quadratic in form, especially this one, okay, we have the possible existence of both real and complex roots, which we have in this case. So we have complex roots with positive and negative 2i, and then we have the real integer solutions with negative and positive 1. And again, another equation quadratic in form, say we have to come about in the form of, in its own capacity, taking the difference of squares. And let's say we have something like x to the fourth minus 81 is equal to 0. Okay, if you notice, we don't have a lower degree x term. Okay, we have just x to the fourth. And x to the fourth minus 81, okay, we can treat this as a difference of squares. So again, from x to the fourth, I can factor out terms in x squared. And we have with minus 81. Okay, we have equal weights in terms of adding and subtracting. Okay, so I have x squared plus 9 and x squared minus 9. And let me kind of mention, I'm going to forgo the complete factoring. Now, x squared plus 9. This particular expression is not factorable. And in the case of the difference of squares, now this one, difference of squares, is factorable. So x squared plus 9, that is already settled as its own factor, and x squared minus 9, you have your option of factoring or not. And let's say that if I bypass factoring x squared minus 9 into x plus and x minus 3, and we just go ahead and set these second order expressions to 0. Okay, so if I set x squared plus 9 equal to 0, and we take 9 away from both ends, so we have x squared equal to negative 9, and if I go from x squared to x, I have x equal to plus or minus the square root of negative 9. Okay, so I have x equal to plus or minus, and the square root of negative 9 becomes 3i. And for x squared minus 9 equal to 0, so if we add 9 to both ends, we have that x squared is equal to 9. And again, with the reapplying of the square root property of equality, we have x equal to plus or minus 9. So you have x equal to plus or minus 3. So again, we have a fourth order equation, meaning that there could possibly be, but not guaranteed as such, 4 solutions. And we have this to also arise. So we have in the full display, so we have for the solutions in x, we have negative 3i and 3i, as well as 3 and negative 3. Okay, so you have 2 complex roots and 2 real roots to make up all 4 solutions. And tell you what, in the case of working with equations that are quadratic in form, and for the present moment, I'm just going to stick with these equations at 4th degree. Okay, let's say we have x to the 4th plus 2x squared plus 1 is equal to 0. And say we'll have next, okay, we'll say we have x to the 4th. And this one I think is going to have irrational roots, but still with a trinomial that can be factored. Let's say we have x to the 4th plus 6x squared minus 16 is equal to 0. And we'll say last, okay, that we have x to the 4th minus 16 is equal to 0. Okay, if you're still working on these items, that is fine. We'll just go ahead and look into the first, okay, of this set. Okay, so we have x to the 4th plus 2x squared plus 1 is equal to 0. And this is going to be a case of an equation quadratic in form that will happen to be a square trinomial. Where if you notice, okay, if you factor, okay, we're going to have x squared plus 1 times itself. So here we're going to have what will be referred to as repeating quadratic factor or repeating second order factor. So you have x squared plus 1 times itself. And so we're going to have for the solutions in x, okay, they will come only from x squared plus 1 set equal to 0. And we have in following through, again, if I isolate x squared, I'm going to have the x squared is equal to -1. And if I go from second to first order, once again, upon utilizing the square root property of equalities, I have x equal to plus or minus, okay, the square root of -1. And so you have x equal to plus or minus I, and itemize in case you have I, as well as -I. So again, with the 4, you might have up to 4 solutions if it's conditional, but if you have circumstances like a repeating linear or quadratic or just a repeating factor period, as was the case in x squared plus 1, that sort of curtails the number of maximum solutions, okay, where in this case, because of the repetition, okay, x was limited to 2 solutions, okay, with I and -I. So there are no real solutions in the mix, just the complex solutions with I and -I. All right, now for what we have in the next equation, okay, we have with x to the 4th plus 6x squared minus 16 is equal to 0. So we have, again, from x to the 4th, okay, this will go to x squared, and factors of -16, whose sum or difference will be on the plus side at 6. Okay, now we're going to have more weight given to the adding than to the subtracting. So here we're going to have x squared plus 8 on the side of addition. And for what we have in the case of subtracting, okay, this will become x squared minus 2. Okay. All right, and so just taking what we have here, okay, so if I set the factors equal to each other, or equal to 0, okay, so you have with x squared plus 8 equal to 0, and if I isolate the x squared term, so I'm going to have the x squared is equal to -8. And if I go from second to first degree in x, so you have plus or minus, okay, the square root of -8. And just incrementally breaking this down, so you have plus or minus the square root of 8 times I. And again, 8, not a perfect square value, but it is a square root, okay, that can be reduced. Okay, so again, square root of 8 had the square root of 4 times the square root of 2. And so we have with x in the reduced radical complex number form. So we have plus or minus 2 times the square root of 2 times I. Okay. Now for the other factor, okay, we have x squared minus 2. And if I set this equal to 0, and this time we have adding 2 to both sides. So you have the x squared is equal to 2, and utilizing the square root property of equality, so I have going from x squared to x, I have equal to plus or minus, okay, the square root of 2, and that is already in simplest radical form. So we're going to have for the solutions in x, okay, we have 2 complex solutions with 2 times the square root of 2i, as well as -2 times the square root of 2 times I. And also we have for the rest, you have in the real irrational roots, we have square root of 2 as well as the negative of the square root of 2. Now, in looking at what we have for the third, okay, so we have again another layout of a difference of squares. And for x to the fourth minus 16, and we have upon factoring, okay, so x to the fourth once again is going to go to x squared times itself for minus 16. And we have plus 4 and minus 4. And if I'm looking at factoring as much as possible, again, I could have gone ahead and set both of these factors to 0, but I'm going to go ahead and completely factor. So we have x squared plus 4, which is locked in. And for x squared minus 4, so this will go to x plus 2 and x minus 2. And now setting each of these factors to 0. Okay, so we have x squared plus 4 equal to 0, and x plus 2 equal to 0, as well as x minus 2 equal to 0. Okay, so we have with x squared plus 4, okay, if I isolate the x squared term, so we're going to have that x squared is equal to negative 4, and applying the square root property of equality. So if we go from x squared to x, and have x equal to plus or minus, okay, the square root of negative 4, and here we're going to have the x equal to plus or minus 2i. And for the linear factors, x plus 2 and x minus 2. For x plus 2 equal to 0, okay, so we're going to have the x is equal to negative 2. And for x minus 2 equal to 0, we're going to have the x is equal to 2. And so we're going to have, just like the second case, the third case is going to have 4 solutions, whereupon we have 2i and negative 2i in the complex domain. And we have for the real solutions, again, we have negative and positive 2. Alright, so in terms of equation solving, we've been on the tangent of working with fourth order equations. And we're going to sort of shift gears. And for the last set of problems, again, I said to be looking into. And this set, within the set, for those items that will come after number 71, we now have with numbers 92 and 93. Okay, we have equations that are quadratic in form, but where we have different degrees. And then on top of that, you're going to have a fixation not just potentially on the square root property of equality, but also with the principal square root rule. And in the case of number 92, okay, so we have in this setup, okay, now we have 3 times d to the 2/3. You have minus d to the 1/3 minus 4, okay, is equal to 0. And if you notice, for the degrees in d, these are non-integer exponents, but still we have 2/3, the higher order, 1/3, the lower degree, and 2/3 to 1/3 is still going to be a 2-to-1 ratio. So we're going to have this equation, okay, to be quadratic. In terms of d to the 1/3, okay, and let me kind of give you something in terms of creating a pathway to factoring this expression out, and I'll give you something that's sort of analogous to what we have here. Okay, say if you have like x to represent d to the 1/3 and x squared to represent d to the 2/3. Okay, so if I have 3x squared minus x minus 4 equal to 0, now if I look at factoring, now 3x squared, okay, 3 is a prime number, and if the expression is factorable and we have the leading term to be 3x squared, we're only going to have 3x and x. Now for the factors of negative 4, I need the right combination such that the outside and the inside products, when you FOIL out, will come out to negative x. And so for what I'm going to have here, I'm going to have minus 4 and plus 1 alongside the x. And I have is equal to 0. And I know I was asking, how did I get to this combination so quickly? But let me kind of mention, say I have 3x and x, and then now for the only possible combinations of 4, I might have had plus 4 minus 1. Or I could have had plus 2 minus 2. I could have had 3x minus 2 and x plus 2. And again, just what the ultimate result was, so it's 3x minus 4 and x plus 1. Now, the reason I decided to go ahead and just kind of use trial and error is that if I did the factoring by grouping, okay, this would be kind of stretched out, especially since we have low number coefficients to begin with. Okay, so we have among these sets, first product, okay, will be 3x squared. Now the last product, okay, you're still going to have it negative 4. Okay, but we need the combination of the outside and the inside products to amount to negative x. And guess what? I got minus 3x plus 4x. So that's going to be a positive x. If I have 3x times negative 2, that's negative 6x. Negative 6x plus 2x is a negative 4x. And then I have 6x minus 2x, so I have a plus 4x. And guess what? You got 3x for the outside, negative 4x for the inside, so you got a negative x. So you had to be careful in terms of the factors here. So 3x plus 4x minus 1, middle term is x, so that strikes out. Here, 3x plus 2x minus 2, middle term, we have a minus 4x, that strikes out. This combination, we have middle term at positive 4x, that strikes out. But with this combination, middle term is negative x, and so that is going to check out. All right, and so just carrying over, okay, one might ask, okay, what does this have to do with the variable d? Well, you had the same coefficients, same weights in terms of the degree comparisons. So if I have x to be represented by d to the 1/3, we have on a parallel course, so like 3 times x, this would be 3 times d to the 1/3. And for x plus 1, okay, this would translate out to d to the 1/3 plus 1 is equal to 0. Okay, so we have a couple of factors in d, and if I set each of these to 0, so I have 3 times d to the 1/3 minus 4 is equal to 0. And I have d to the 1/3 plus 1 is equal to 0. And if I isolate the variable terms, okay, so first factor, okay, so I'm adding 4 to both sides, and if I look at solving for d, if I can, we had that 3d to the 1/3 is equal to 4, and then isolating d to the 1/3. Okay, so if I divide by 3, so I have that d to the 1/3 is equal to 4/3. And again, just kind of going back to the converting between radicals and non-integer exponents. Now d to the 1/3, okay, this is going to be the cubic root of d. Okay, so the cubic root of d is equal to 4/3. And then taking care of the radical upon applying both sides and cubing, okay, so the cubic root of d cubed, okay, this will come out to d. 4/3 to the third. 4 cubed is 64, 3 cubed is 27. So we have, for the first solution in d, this will come out to positive 64/27. Now, for the other factor, for d to the 1/3 plus 1 equal to 0, if I take 1 away from both sides, okay, so I have d to the 1/3 is equal to -1. And just rewriting as a radical. So d to the 1/3. Okay, so this is going to be the cubic root of d is equal to -1. Okay, and let me pause right there. Again, if I had an even root, like square root, fourth root, sixth root, and this had to be set equal to -1, there would be no solution, again, on the basis of the principal square root rule. But since I have an odd root instead, and I can reduce odd root radicals to negative constants, so I can arrive at a solution in d for this one. Okay, so we have, upon cubing both sides, so the cubic root of d to the third, this will come out to d, and -1 cubed, -1 times itself, this will come out to -1. So here we're going to have two solutions in d. One we have at 64/27, and the other we have at -1. Okay. All right, and here, so you have two solutions, and both of these happen to be real values. Okay. Now, for what we have in the case of number 93, we have another equation, okay, that is going to be quadratic in form. So for 93, okay, this time we have the equation in terms of the variable n, whereupon we have n to the 1/2 plus 6 times n to the 1/4, and we have -16 is equal to 0. Now, if you notice, for the degrees in n, you have 1/2 for the higher order, 1/4 for the lower. Okay, so you still have a 2-to-1 ratio. So this equation, you have quadratic in terms of n to the 1/4. And just as something analogous here, like if I had, so I have n to the 1/2, like if you have like n squared or x squared, however you do it. I'm just going to keep just kind of match the letters here. If I have like n squared plus 6n minus 16 is equal to 0. I will have, for the factors, I have like n plus 8 and n minus 2 equal to 0. Okay, but here you're going to have, again, the higher order, like the square will reference n to the 1/2, and n first order will reference n to the 1/4. So you have just on the parallel, okay, whatever the equation is quadratic n, this will be what I'm going to factor. So for n to the 1/2, this will factor out, just as n squared factors out to n and n to the 1/2 will factor out to n to the 1/4 and itself. And then factors of -16, whose sum or difference will be 6. We're going to have +8 and -2. And so for what we have in the setup, okay, we have with the zero product property, if I set the factors each to 0, okay, so for n to the 1/4 plus 8 is equal to 0, if I isolate n to the 1/4, so I have the n to the 1/4 is equal to -8, and if I rewrite n to the 1/4 as its radical equivalent, now I have the 4th root of n is equal to -8. Okay, this time, okay, I'm dealing with an even root radical, and this is where the principal square root rule will be of concern. Again, the even root of an expression cannot reduce to a negative constant. Well, guess what? I have the even root, in this case, the 4th root of n set equal to -8, and because of this negative sign, okay, this portion is not going to have a solution. And so the only possible chance of there being a solution for n is going to come from the other factor. And so we have for n to the 1/4 -2 equal to 0. If I isolate the variable term upon adding 2 to both sides, so I have n to the 1/4 is equal to 2. And rewriting as a radical, so I have the 4th root of n is equal to 2, and here I have an even root that goes to 2, and 2 being a non-negative constant, I can follow through and take both sides and raise to the 4th power. Again, the 4th root of n raised to the 4th. Again, the exponent and the radical go out, so you have n. And then for 2 to the 4th, that's 2 times itself, times itself, times itself. And for this result, okay, we have that n is equal to 16. And we will be looking into further cases of equations quadratic in form. And now, just kind of shifting over, and we have for items in the future section, R.8. Okay, we'll be looking into inequalities of various types. And for what we have in the case of inequalities, okay, there'll be varieties of notations that will be used. Okay, and kind of starting from here and going on out, okay, you'll have what will be referred to as interval notation, and then give you just some examples of inequalities. And let's say we have that x is greater than 2. And I want to represent this statement in the form of a number line. Okay, so there'll be some activity going on. Okay, and yeah, that should do it. Okay, and for what we have in the case of a number line. Okay, so I have the x is greater than 2. Now for inequality statements like greater than, less than, the author will have like the use of a parenthesis in the book. But now in Alex, instead of parenthesis, it's going to be an open circle, or what is also referred to as a hole. And we have for x is greater than 2. Now 2 is not included. So we have representing the activity starting from, let's say, the value that is tangent to, but not including 2. Okay, we have an open circle or a hole, and then we have x is going to be greater than 2. So if I represent what we have for x is greater than 2, I'm going to have an array that's going to go out to the right, where the values of x are going to be increasing. And just representing what we have here. Okay, so you have an array that's going to go out to the right, and the interval notation we have here. Interval notation will have like parentheses and or brackets. And for x is greater than 2, so you're going to start tangent to 2, but not including 2. So the exclusion of 2 is going to be indicated by a parenthesis, and then continuously going out to the right. So we have going out to positive infinity, and infinity is going to be also in parentheses, because infinity is like it's a concept like you have continuous expansion, and there's no endpoint with infinity. So that's the reason this stays in a parenthesis, like negative and positive infinity. Think of it like an expanding universe. It never stops expanding theoretically, and so you're looking at negative and positive infinity as no particular stopping point. And if we have, let's say, as another inequality, that x is greater than or equal to -1. So have for this number line, so have x is greater than or equal to -1. So with the equal sign, this means that x equals -1 is part of the system. So we have on -1, instead of an open circle, we're going to have a closed point. And the rest of the values will be greater than -1. So again, we'll have the direction of the activity out to the right. And for the interval notation, okay, so we're going from and including -1. And the inclusion of -1 is going to be symbolized by a bracket enclosing -1. And then we have a continuous increase from the negative to 0 to the positive, and again continuously increasing. So we have going out and approaching infinity. And let's say that if we still maintain the use of one direction inequalities in this time, we'll say that we have that x is less than 0. Okay, so for x is less than 0, okay, so 0 is not included, so we have a hole or open circle on 0. And for the rest of the values, okay, for those values of x less than 0, you're now going to have an array that is going to go to the left. And for the interval notation on this one, okay, this time reading in order from left to right, so the lower limits can have it continuously in the other direction, where we have negative infinity. And for the upper limits, okay, we have approaching but not including 0. And if we have, let's say, another single direction inequality, if I have that x is less than or equal to 5, okay, so for x is less than or equal to 5, excuse me. Hello? I'm teaching class. Sorry. For x is less than or equal to 5, okay, so you're going to have a close point on 5. Now we have a ray that is going out to the left. Okay, and so we have with the interval notation, okay, so we have going from negative infinity, okay, and then we have approaching and including the value of 5. Okay, and then we have another saying. So far we've had the direction to indicate either continuous increase or continuous decrease. But now let's say if we have x to be the set of all real numbers. Okay, so for all real numbers, okay, you're looking at including the positives, the negatives, the zeros, the rational roots, the irrational roots. And so for what we're going to have here, you have continuous activity going from end to end. And for what we have in interval terms, okay, so we have going non-stop between negative and positive infinity. And again, the infinities, negative and positive, okay, are going to be boundless. And so we'll have contained in parentheses. So anytime you see negative, positive, infinity in parentheses, you're making reference to the set of all real numbers. And then if you have, let's see, a case where you don't have continuous activity in either direction, and we'll say that we have something like a compound inequality statement, where we say that we have something like negative 3 is less than or equal to x. Which in turn is going to be less than 2. Okay, so in terms of the notations to place on this graph, so you have negative 3 is less than or equal to x. Same logically as x is greater than or equal to negative 3. So the inclusion of the equal sign means that negative 3 is part of the set, and that's going to be indicated by a close point. And then we have, for the other half of this compound inequality, we have the x is less than 2, 2 is not included, and that's going to be, the exclusion is going to be indicated by an open circle. And then for everything else in x, okay, this will connect the point on negative 3 to the hole that we have applied to 2. And so we have connecting. Okay, we're going to have, instead of a ray going to the right or to the left, or a line running endlessly, okay, we're going to have a line segment. And for the interval notation representing this, okay, so you have between -3 and +2. And once again, -3 is included, and that's going to be indicated by the bracket. And with 2 left out, we have 2 in the parentheses. So you're looking at going, say, starting at -3, and then you have like your endpoint would be like 1.99999, but never exactly getting to 2. All right, so these are samples of what we have with inequality statements, and we'll be looking into situations of officially solving for inequalities, and give you just some samples here, crossing over into absolute value. Okay, and just sort of carrying over the k and the absolute value of x, okay, from when we looked into absolute value equations. Okay, so if we have that k is a non-negative value, and we have that the absolute value of x is equal to k, okay, then we're going to have that x is equal to plus or minus k, and just itemizing, so we have k as well as negative k. And this goes back to when we were looking into absolute value equations. Now, in the case of crossing over to the realm of inequalities, if we have that the absolute value of x is less than k, then what's going to happen here, if your inequality is in the direction of less than or equal to k, once you take out the absolute value bars, you're going to have x to lie between negative and positive k. And just the interval notation for this, so for x is between negative and positive k, you would have like parentheses enclosing negative and positive k. And if I have it that the absolute value of x is less than or equal to k, again, you have a compound inequality, and you have that negative k is less than or equal to x, is less than or equal to k, and again, with the equal signs, this will indicate that the solution set in x would have in the interval notation brackets around minus and positive k. And if we have the inequality to go such that we have greater than or equal to k. Okay, so if we had that the absolute value of x is greater than k, what's going to happen here? Okay, remember, absolute value refers to distance away from 0. Okay, and when we have like if you have less than k, okay, that means that you have getting closer to 0 from both ends. Think of it kind of like magnetism. But if we're looking at greater than k, think of it like, instead of magnetism, think of it like repulsion, increasingly negative, increasingly positive. So you're going to have x to branch out into opposing directions once x is taken out of the absolute value bars. So you might have at the lower end that x is going to be less than negative k, but it might be that x is going to be increasing at the positive end of the spectrum, where we have that x is greater than k. And in terms of what the interval notation would look like for this, for x is less than negative k, we'd have like going from negative infinity and approaching but not including negative k. And then at the other ends, you have where x is greater than k. You have starting past k, that is starting past positive k and going out to infinity. And that U symbol, that is in the middle. U refers to union of sets or intervals. And then we have with the remaining possible case about the absolute value of x. And if this is greater than or equal to k, you'll have the same kind of dynamic direction-wise to apply. Okay, so we'll have that x is less than or equal to negative k, or that x is greater than or equal to k. And just the interval notation equivalents we have from negative infinity approaching and including negative k. So we have negative k is going to be in the brackets. And then we have at the other end, we have going from and including k and heading on out to infinity. Okay. And let's say that if we have just as examples, just sort of kick things off with absolute value inequalities. And let's say if we have say if I were to determine the interval solutions for x. Okay, so for the interval solutions for x, okay, if we have as first item, okay, and I'm just going to work around, let's say just kind of get us started off once again. If I have the absolute value of x minus 1 is less than or equal to 7. Okay, so I have the absolute value of x minus 1 is less than or equal to 7. Okay, so think of the absolute value of x, where x is represented by x minus 1, and k is represented by 7, which is a non-negative value. And in terms of which of these applications will apply, so the direction of the inequality have in the absolute value have less than or equal to k. So we're looking at this particular dynamic that will be carried out. And we have that if the absolute value of x is less than or equal to k, once you take the absolute value notation out, so we have the character or characters inside will be sandwiched between the negative and positive of those values representing k. So we have for the dynamic that is going to be carried out, so for the absolute value of x minus 1 is less than or equal to 7, we're going to have that negative 7 is less than or equal to x minus 1, which in turn is going to be less than or equal to 7. Again, so you have x represented by x minus 1, negative and positive k represented by negative and positive 7. And I'm looking at solving for x. So if I get the x in the middle by itself, so I'm going to add 1 not only to x minus 1 but to all sections of this compound inequality. So we have in the result Okay, negative 7 plus 1 becomes negative 6. And then in turn we have is less than or equal to x, which in turn is going to be less than or equal to 8. Okay, so this is our compound inequality solution. So we have negative 6 is less than or equal to x is less than or equal to 8. And for the interval solution, okay, so you have between negative 6 and 8 inclusively. So negative 6 is included thanks to the equal sign, and likewise thanks to the equal sign 8 is also included. So we're going to have both negative 6 and 8 in the brackets. And say we have in the final case, and still working around the absolute value of x minus 1. If I have it that the absolute value of x minus 1 is greater than 7. Okay, so looking at the nature, so again, x minus 1 represents x, 7 represents k. So for what we have here, we have the representation of the absolute value of x is greater than k. So once we take the absolute value notation out, again, we're going to have inequalities that will go in opposite directions. Okay, so we have at the lower end representing x is less than negative k, and we have that x minus 1 is less than negative 7, and the other possibility is where we have x is greater than k is going to be represented by x minus 1 is greater than 7. And for what we have in the case of isolating x for both of these inequalities, so if I add 1, so I have that x is less than negative 6, or that x is greater than 8. Okay, so this is our inequality solution combination. And once again, if I express in interval solution terms, okay, so for x is less than negative 6 for this part. Okay, so we're going to have going from negative infinity, approaching but not including negative 6, so I have parentheses here. Then for the other half, okay, we have in union with a set of values x greater than 8 and just the symbolic interval notation for x is greater than 8. So we have starting out with a parenthesis around 8, and the rest of the values, okay, have increasing, and we have approaching infinity. And again, infinities are boundless, and they remain in parentheses throughout. Now for items to go ahead and be looking into, and again we have the class activity 1, which is available in ALEX, and that will be due tomorrow night at 11:59 p.m. And again, the ALEX homeworks sections R6 and R8 will be due respectively on Monday night and Wednesday night. And again, I do have video simulations available in the weekly notes tab. And for what we have concerning the inequalities, those general and those with absolute value, go ahead and be looking on pages 102 and 103, exercises 9, 10, 16, 27, 28, 48, and number 58.